Welcome to Chapter 8. In Section 8.1, we are looking at general theory for linear differential equations. So the first thing that we're going to do is we're going to develop some notation that we're going to be using for these differential equations. So we need to define the derivative operator. The derivative operator is labeled as d from c1 of I to c0 of I, where c1 consists of differentiable functions on the interval I, and c0 consists of continuous functions on the interval I. So what d is doing is it's basically performing a derivative. So this is how we're defining d. So d of a function is just the derivative of that function, hence the derivative operator. So it's performing the operation of a derivative upon a function that gives us f prime. And in general, we can define dk as being the kth derivative of a function, going from ck to c0. So, for example, if we wanted to take the third derivative, we would have d cubed, right? D to the third. That would be taking us from third differentiable, so 3 times differentiable functions, taking the derivative 3 times until we get down to the continuous functions. Okay, and that would give us f triple prime up here. And so on and so forth for any value of k that we want. So we're going to be using the derivative operator to signify derivatives being taken because it's going to simplify our notation greatly. Instead of writing y's with primes or that derivative notation, we're going to see the d values are a little bit more straightforward to write. So these sets here where we have the differentiable functions, continuous functions, twice differentiable, 3 times differentiable functions, these sets are in fact vector spaces. And D is a linear transformation. So D is essentially transforming a vector, if you will, that would be a function, from c1 to c0. By taking the derivative, we're transforming a differentiable function into a continuous function. Or if we're taking, 5 derivatives, we take a 5 times differentiable function, take its derivative 5 times, and turn it into that continuous function. So we do have vector spaces, vector space properties, and linear transformation properties. Now, the general form for an nth order linear differential equation is something that looks like this. So we have a naught of x, y to the nth derivative, plus a1 of x, y to the n minus 1 derivative, etc., all the way down a sub n of x, y with no derivatives, right? We have second derivative, first derivative, no derivatives right there, equals some unknown function f of x. So this is a linear differential equation, okay, because there's no additional terms or powers applied to the y's, and it is nth order because the highest derivative being taken is n. We can rewrite this using our new differential derivative operator notation. So this is going to be a naught d to the n plus a1 d to the n minus 1, etc. This will be a sub n minus 1 d plus a sub n, which the y itself would be like d to the 0 because there are no derivatives, so that would just not show up. And then we take that of y equals f of x, which a lot of times we'll just abbreviate as f, because the implication is that everything here is ultimately in terms of x. So, but this is the alternative notation we have for something like this, for an nth order linear differential equation. This expression, so when we say this expression, that's this expression. So this expression is called L. That is the linear differential operator. Because this is the general form of a linear differential equation. So this whole expression is our linear differential operator of order n. So the shorthand that you'll often see used for these expressions, instead of this of y equals f, we just put L of y. So L of y equals f. And note, since D is a linear transformation, so is L. So L still is imbued with those properties of the linear transformation. And this is just our shorthand, essentially just going back to this. So this is our way of writing a linear differential equation in short form. Now, what does that look like in practice? Well, if we take this example right here, so we have L is x minus x squared d squared plus sine of x d plus 2x plus e to the x, and y is the function e to the 3x plus 2x, and it says compute L of y. So it's basically saying, like, here's L of y, like in this form in terms of like d squared and d. Now it's asking us to find basically this original version. So if we rewrite this in terms of y's, so we get x minus x squared, d squared is just y double prime, and then sine of x, d is just y prime, that's the first derivative, plus 2x plus e to the x times y. And we know what y is, so we can go ahead and substitute y into here, take its derivative here, take its second derivative there. So we're going to get L of y equals, that's x minus x squared. The first derivative of this would be 3e to the 3x plus 2. The second derivative will be 9e to the 3x and then 0. So that's 9e to the 3x plus sine of x times 3e to the 3x plus 2 plus 2x plus e to the x times e to the 3x plus 2x. So this is the kind of general expanded form of the differential equation. So this version of L of y and this version of L are equivalent to each other. They represent the same thing, but again, the D notation and the L notation gives us kind of this shorthand so that we don't have to write it out expanded like this every single time. Now, to look at some solutions that we're going to be able to get. Since L is a linear transformation, it does have a kernel. So this is the kernel of L. So this is the set of all values of y such that L of y equals 0, right? So when we transform the y, it should transform into 0. That's how we define the kernel of a linear transformation. So we're going to look at how we can find solutions to this, okay, to find elements of the kernel. So given a differential equation, L of y equals f, the associated homogeneous differential equation is L of y equals 0. So we're not at this moment looking at the general solution where it's equal to a function f. We're looking specifically at the homogeneous differential equation, L of y equals 0. So the set of solutions to L of y equals 0, which in other words is the kernel, is a vector space. So the solution set to this is a vector space of dimension n, where L, of course, is equal to a naught d to the n plus a1 d to the n minus 1, etc., to a n minus 1 d plus a n. So if we take a look at an example, solve d squared plus 1 of y equals 0. So let's translate that into a kind of more traditional looking differential equation. So d squared of y, that's just the second derivative of y, so that's y double prime. And then 1 of y, so that's just y equals 0. So this is the equation it's asking us to solve. Now, we can find a couple of solutions to this relatively quickly. If we think about a function, when you add it to its own second derivative, gives you 0. One example, so this would be y1 of x, is sine of x. Right? Sine of x, and then the second derivative is negative sine of x, so those add up to 0. Sticking in the same vein here, y2 of x could be cosine of x. Again, it's cosine, its second derivative is negative cosine, so they would cancel to 0. Now, we know that the kernel, so the vector space that we're creating, is a dimension n, which is whatever the highest order is of the derivatives here. So in this case, because this is second order, we know that the kernel will have a dimension of 2. Okay, so we know kernel of L has dimension 2 here. So the kernel is just going to be, we have two solutions here, two unique solutions, two Li solutions, sine and cosine, right? They're not multiples of each other or linear combinations of each other. So the kernel will just be the span of sine of x and cosine of x. So what this tells us is every solution that we could get for this differential equation will be some linear combination of sine of x and cosine of x. So we can go ahead and set up that linear combination to get the general form of our solution. So every solution of the differential equation above has the form y of x equals c1 times sine of x plus c2 times cosine of x. Because again, the kernel is the span of those two. So any solution to this differential equation will be some linear combination of sine of x and cosine of x. So this will give us a general solution to the differential equation. Moving forward into section 8.2, we're looking at constant coefficient homogeneous linear differential equations. So our titles just keep getting longer and longer as we go. So constant coefficient homogeneous linear differential equations. So given n solutions, y1 through yn, of a differential equation, how can we tell if this set is Li? So like we just saw in that last example, we had two solutions that we created the linear combination of, and we know that those two are Li because sine and cosine clearly are Li to each other. But we want a definitive test. I don't want to just be guessing or saying it looks like it's Li. I want to definitively know whether they are or not. So how do we make this determination? The answer is called the Wronskian. The Wronskian is abbreviated with a capital W, W of y1 through yn. That is the determinant of all of the derivatives of the solutions to that system, to that differential equation. So basically you take the solutions in the first row, and then down the columns you take every applicable derivative of those solutions. Once you have that matrix set up, take its determinant, and this is going to give us the result that we're looking for. So what is that result? Well, let's look really quickly at the example we just did. The Wronskian of sine of x and cosine of x. So that would be the determinant of, so we would have the first one and the second one, along with their derivatives. So that's cosine of x and negative sine of x. Take the determinant. That's negative sine squared x minus cosine squared x, which factor out the negative 1, and you're left with sine squared plus cosine squared, which is just 1. So we get a Wronskian of negative 1 for sine and cosine. How do we know whether that tells us Li or not? Well, this theorem right here will tell us. If there is a value of x, say x naught, such that the Wronskian is non-zero, then this set of solutions is Li. So if there is a value of x, say x naught, where the Wronskian is non-zero, then the solution sets are, the solution set is Li, right? All of the solutions are Li from each other. So this means that we need, if the solution set can be made non-zero for any value of x, the solution will be Li. It would have to be definitively equal to 0 for all x in order for it to be LD. So we can use the Wronskian to help determine if our solutions are Li or if we need to eliminate any extra dependencies among the solution set. Now, looking at the nth order linear constant coefficient homogeneous differential equations. So we're looking at nth order linear. So that's the same thing that we were just talking about, constant coefficient. So of course, constant coefficients, homogeneous. So the system set equal to 0, and then differential equations, of course. So we're looking at L of y equals 0. Okay, so these are the solutions from the kernel of L, an n-dimensional vector space, and we have this general notation, right, that we introduced in the last section. So we're looking at solving more of those types of problems. Since we're dealing with constant coefficients, the solution set, we actually can benefit from past work of people who have already found solutions to these problems. So we're kind of riding their coattails, so to speak. We develop a trial solution that is y equals e to the rx. This is going to form the foundation of our solutions to this type of differential equation. So if we took this as a trial solution and substituted it into the differential equation, so this one up above here, we would get, so like a of n times y, and then a n minus 1 y prime. So that's e to the rx times r again. And then the second derivative would just give us r squared. The third derivative would give us r cubed, etc., etc., etc. We get up here, we have e to the rx times r to the n minus 1, because we took n minus 1 derivatives. And then when we take n derivatives, we end up getting an r to the n showing up in this term. So that's what happens when we substitute this trial solution into that differential equation. And we can factor out e to the rx from all of those terms. So get that out to the front here. This expression in here, okay, where the e to the rx is moved away, and we're looking at the solution to this. This is called the auxiliary polynomial. This is the auxiliary polynomial. And when it comes to finding solutions to this equation here, notice e to the rx will never be equal to 0 because it's an exponential function. There's no value of r or x that will make this 0. So when we're solving for r to figure out like what specific numbers go into this solution, we only need to solve the auxiliary polynomial. This is the only part that will actually make this equal to 0. So there will be n solutions for r, okay, because we have an nth degree polynomial here. So we're going to set this part only equal to 0. That gives us the auxiliary equation, which is just the auxiliary polynomial set equal to 0. Any values of r that solve this equation provide a solution to the differential equation. Okay, so again, we had the differential equation. We take a trial solution that's provided to us. We test it in the differential equation. We get this general form, and we say, okay, well, if this is going to be a solution, this part has to be equal to 0. So we set that equal to 0. That's our auxiliary equation. And now we can solve this equation for r values that when we plug them into this e to the rx, makes that a solution to the differential equation. So let's take a look at an example. So find the general solution to d minus 2 times d squared minus 16, all of y equals 0. So if we were writing this out in our traditional like functional notation and prime notation, if you like FOIL this out, like expand all of this out, you would get a d cubed, you would get a minus 2d squared, minus 16d, and then plus 32. All of that would translate to y triple prime minus 2y double prime minus 16y prime plus 32y equals 0. So when it's asking us to find the general solution to this differential equation, it's really asking us to find the solution to this. But notationally, we're not going to work with it this way. We're going to work with it using d, that derivative operator. So what we're looking at here is this equation getting translated into this equation, which essentially, if you look at how this translates, the d to the n becomes r to the n, d to the n minus 1 becomes r to the n minus 1, etc., etc., etc. So by using this form of the solution, all we need to do is turn these into r's. So we get r minus 2 times r squared minus 16 equals 0. Okay, so this is our auxiliary equation. and we're trying to come up with solutions to this, which there are 3, right? Because this is already perfectly factored, so we're going to get r equals 2, r equals 4, and r equals -4. So these 3 values of r provide us with 3 possible solutions to the differential equation. So we have y1 of x equals e to the 2x, y2 of x is e to the 4x, and y3 of x is e to the -4x. So these are our 3 individual solutions. Now the question is, are these solutions linearly independent from each other? We can verify this by taking the Wronskian, because if we do have a linearly dependent relationship, we would need to eliminate any of those dependencies to make our solution as efficient as possible. So we're going to have e to the 2x, e to the 4x, e to the -4x, and then take derivatives down the columns. So 2e to the 2x, 4e to the 4x, -4e to the -4x. Then we get 4e to the 2x, 16e to the 4x, and 16e to the -4x. Compute the determinant of this using any of those methods necessary for 3x3s. This one, probably looking at maybe using like the arrow method or like traditional cross product method. Cofactor expansion is not necessarily the easiest one to do here just because there are no zeros at all, but you can still use any of those methods and they'll all still apply. But we end up getting 96e to the 2x as the value of the determinant. And this is not equal to 0, right? And actually there is no number we could plug in to make that equal to 0 regardless. So that means these solutions are Li. So in other words, we need all of them. There are no unnecessary dependencies here. So the general solution to the differential equation is going to be y of x equals c1 e to the 2x plus c2 e to the 4x plus c3 e to the -4x. So any solution to this differential equation, or if you like, this differential equation, must be written as a linear combination of these 3 solutions in some way or another. And you can pick different values and actually try like taking the derivatives. Like if you wanted to test this, you could take the function with specific values, take its derivative, take its second derivative, and take its third derivative and plug them all into this equation. And you would see that you get 0 as the kind of validation that it is in fact the correct solution. Let's take a look at another example. So find the general solution to this differential equation, y triple prime minus y double prime minus 30y prime equals 0. So if we translate that into our derivative operator notation, that's d cubed minus d squared minus 30d of y equals 0. And now we'll translate that into the auxiliary equation. So that's going to be r cubed minus r squared minus 30r equals 0. Factor out an r. That leaves us with r squared minus r minus 30, which does factor as r minus 6 and r minus 5. So we get r is 0, 6, and -5. So we're going to have our three potential solutions here. So y1, it'll be, so that's e to the 0, so that's just 1. y2 will be e to the 6x, and y3 be e to the negative 5x. Verify linear independence with the Wronskian. 1 e to the 6x, e to the negative 5x. Derivative is 0 and 0. We get 6 e to the 6x and 36 e to the 6x. We get negative 5 e to the negative 5x and 25 e to the negative 5x. This one is a little bit simpler because of these zeros here, but we end up getting 330 e to the x, which is non-zero. Okay, so these are Li, and thus form a basis for the kernel of L of solutions, right? Because the kernel contains all the solutions to this homogeneous differential equation. So because this forms a basis and all of the terms are Li, the general solution will cover any solution to this differential equation. So our general solution will be y of x equals c1 times 1 plus c2 e to the 6x plus c3 e to the negative 5x. So that would be the solution, the general solution to this differential equation. Now, when it comes to working with this type of differential equation, there are two issues primarily that we have to take into consideration. Because when we're solving, we're turning the differential equation with these derivative operators into the auxiliary polynomial and then the auxiliary equation. And then we're solving that. The issue, or the two issues that can come up that have not yet, are the issues of repeated roots to the auxiliary equation. So you can have a value of r showing up more than once, and you can have complex roots to the auxiliary equation. So maybe the auxiliary equation doesn't factor well, and it doesn't factor with integers. If we need complex numbers or imaginary numbers in our solution, that's going to change slightly what our solution looks like. So how do we handle these cases? Well, case one is pretty straightforward. If a root r is repeated k times, we get k Li solutions as follows. So the original solution is y equals e to the rx. The second solution is y equals x e to the rx, and then x squared e to the rx, x cubed e to the rx, etc., 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 all the way to x to the k minus 1 times e to the rx. So a repeated root, we take the same form of the solution but multiply by another factor of x. That makes the solutions Li from each other, makes them distinct. So if we had a root that repeated itself 3 times, we would get, like e to the rx, y equals x e to the rx, and y equals x squared e to the rx as 3 separate solutions, one corresponding to each value. If we have complex roots, so if r equals a plus bi, where b is non-zero, because if b was 0, it's not complex anymore, then the complex conjugate is also a root. So if a plus bi is a root, a minus bi is also a root. Now, when we set up the general form of the solution here, so y1, that's e to the rx, so we get e to the a plus bix, which when we split up like this, we get e to the ax times e to the ibx. And then same thing for the second one with the conjugate, we get e to the ax and e to the negative ibx. But we want to develop a form of solution that does not involve complex values. And in fact, that is something we can do. We're going to need a little bit of help. And we can find this using what we call Euler's formula. So Euler was a brilliant mathematician from a couple hundred years ago who developed a lot of these different processes that we still use today in many different fields of mathematics. But one of his most well-known results is Euler's formula, and it derives a connection between exponential functions and trig functions, and all tied together with imaginary numbers. So Euler's formula says e to the I times theta is equal to cosine of theta plus I sine of theta. Interesting thing, this formula can actually be derived using either infinite series or integration. So you can see like Calc 1, Calc 2 methods of solution for this, just also incorporating the imaginary numbers into it. As just a little bit of a tangent, one interesting result from this formula is Euler's identity. This is often considered to be the most beautiful formula in all of mathematics, and that is this relationship, e to the I pi plus 1 equals 0, which is fairly easy to derive if you just let theta be pi and then move things around a little bit. This is the result that you get. This equation is so prominent in mathematics visually because it incorporates 5 of the most important constants in all of mathematics together in one equation. So we've got e, we've got I, we've got pi, we've got 1, and we've got 0, right? With e, of course, being that natural exponential base, I representing all complex numbers, pi being a representation of so many things in trigonometry and all of that stuff, 1 being the multiplicative identity and 0 being the additive identity. So many different kind of important terms all in this very simple, concise relationship. And that is a direct result of Euler's formula. Not something that we're necessarily going to be using in here, but just an interesting result nonetheless. So using Euler's formula, we get, instead of e to the ibx for our first solution, so these got relabeled as W1 and W2 because we're just using them as placeholders at the moment. We're going to develop the final solutions in a second. But we go ahead and replace e to the ibx with this. Okay, so instead we have I and theta is getting replaced by bx. So we get cosine of bx plus I sine of bx. And then same thing for the second one. Instead of e to the negative ibx, we're going to get cosine of negative bx and I sine of negative bx. But because of the evenness and oddness of the cosine and sine functions, we know with cosine you can get rid of the negative entirely, and it's the same. With sine, you can pull the negative out, and it's the same. So this is equivalent to this. So these are two different forms of the solution, but since these are both solutions, any linear combination of them is also a solution. So to simplify our work as much as possible, consider the following. So any linear combination of these will be a solution to this differential equation. We want to pick as simple a form as we possibly can for our solution. So for our first solution, y1, we take w1 plus w2 divided by 2. So We will have e to the ax still, and we can just factor that out of both of these, and we'll have cosine of bx plus cosine of bx, so that's 2 cosine of bx, plus I sine minus I sine, so those are gone. So we have 2 cosine, and then divide by 2, we just get cosine of bx. And this would be an element of the kernel of L. Okay, in other words, a solution to the differential equation. And then we can try taking W1 minus W2 all over 2. So e to the ax will still be there out in the front. Now when we subtract, we get cosine minus cosine. And we get I sine minus negative I sine. So we're going to end up getting a 2 that then subtracts, or excuse me, that then divides, and that gives us sine of bx, which is also an element of the kernel. All right. So using these as our solutions, we can then apply this to any form of complex solution to the auxiliary equation. So if we have repeated roots, we can use this form. If we have complex roots, we can use this form of the solution, where a and b are just the components of that complex expression. So let's take a look at an example. So we have d squared plus 4 quantity squared times d plus 1 quantity cubed of y equals 0. So convert to the auxiliary equation. So r squared plus 4 squared times r plus 1 cubed equals 0. This first one will give us a complex solution that's going to be right, if you subtract that over, you get r squared equals negative 4. So r is going to be plus or minus 2i, each one having a multiplicity of 2. And this one solves normally. We got r equals negative 1, but it has a multiplicity of 3. So really, if we look at all of the roots here, so we have a negative 2i, a negative 2i, a 2i, a 2i, a negative 1, a negative 1, and a negative 1. So we've got not only complex roots, not only repeated roots, but also repeated complex roots. So all of these complex roots, by the way, the a value is 0 and the b value is 2. Right, because it's a plus or minus bi. So our general solution is going to be, for the complex, we're going to have c1 cosine of 2x plus c2 sine of 2x. Okay, so that's the first pair. But then for the repeated roots, we just introduce a factor of x in front of each one. So that's c3 x cosine of 2x plus c4 x sine of 2x. Okay, so these two are repeated roots. Those two are repeated roots. We just introduce that x factor in front of them. And then for the negative 1s, it repeats itself 3 times. So we get C5 e to the negative x. Let me shrink this down just a little bit. Plus C6 x e to the negative x plus C7 x squared e to the negative x. And that would be the general solution to this differential equation. Everything in terms of sines, cosines, e to the negative x's. Because of those 7 roots that we have 7 solutions here. All right, let's try one more. Solve this differential equation, d squared minus 6d plus 13 quantity squared of y equals 0. So we get r squared minus 6r plus 13 quantity squared equals 0. This is not factorable. 13 is prime, so you can't break that up in any realistic way. So we get r is 6 plus or minus square root of b squared minus 4ac. So that's minus 52 all over 2a. So it's quadratic formula. So we get 6 plus or minus, that gives us a negative 16. So that's 4i all over 2. So 3 plus or minus 2i. So our roots will be 3 plus or minus 2i, which produces 2 solutions in and of itself, but the whole quantity was also squared. So it's actually a multiplicity of 2 on both of them. So we'll have 4 roots, okay? Or in other words, 4 solutions to the differential equation. So we end up getting, so we have a is 3 and b is 2. So we get c1 e to the 3x cosine of 2x plus c2 e to the 3x sine of 2x plus c3 x e to the 3x cosine of 2x plus c4 x e to the 3x sine of 2x. Okay. So we have the first pair of solutions, so that's the plus and the minus case. Give us these, right, where we have e to the ax and cosine of bx, e to the ax sine of bx for those. And then this one gets repeated, so we get the x here. And then this one gets repeated, so in this one we have the x there. Okay, so we have the case of the complex pairs and their repeated roots right there. That produces 4 individual components to the solution to this differential equation. And that brings us to the end of section 8.2 and our introduction into, of course, solving a lot more different types of differential equations. When we come back later in the chapter, we're going to be looking at more types of equations and not just looking at the homogeneous cases like we have been so far. We'll see what that looks like when we return.